Okay, looks like we'll make a start. Just had some technical troubles there, but I think we're good now. Alrighty. First of all, I apologise if I sound a bit croaky. I've managed to pick up a cold in the last 24 hours. I've also got my young son making a bit of noise in another room, but that's all right. We'll push through and get into talking about validation and how validation applies in the engineering design process, and how we can apply it in Enduro Student and similar sort of design events. And then finally some specific information about the validation competition event at ESR 2020. Alrighty. So validation in the design process. So first of all, we'll just sort of recap something a bit with the design process that hopefully most of you are familiar with from your engineering classes. So really in design engineering, we're trying to solve a problem by designing an object, whether that's a part or an assembly or a process, maybe for example a chemical process. It doesn't really matter, but the main thing we're trying to do is basically solve this problem. And so first of all, what you would have been taught in your classes, of course, is we have to accurately define the problem first. And we'll just focus on a couple of things here because these are going to come up as important later on when it comes to your validation. So first of all, being precise, that is to condense sort of general target behaviours down to actual concrete numbers. So for example, is the overall behaviour we're after is that the engine mounts or the chassis must not harmonise with the engine, for example, the engine vibration. But this is not really enough. It's not enough to design those parts around. It's also not enough to give us validation options later on. You end up being caught with a part that just sort of kind of does the job, but we don't know how to validate it because it was never really designed around concrete targets to start with. So a better example there is really breaking it down to the actual numbers that this behaviour is going to depend on. So for example, expressing it as, say, excitation from the engine between 800 to 2,500 RPM, going through the engine vibration isolation, must not result in amplitude transfer above a factor of 0.1. So that's a nice concrete listing of the numbers we're after to design this object. And it's really important to design it and then also to validate it later. Another note there is to watch out for pass-fail goals. I know it's easy to think of the vehicle as needing to do a job and not fail. It needs to just pass and do the job. But again, you can design a vehicle to do that by making it stronger and stronger until it doesn't break, and then great, you've got something that doesn't fail. But again, it will come back to bite us later on when we try and do validation. So example there, the drive shaft must not break. That's not good enough. We need to design it with actual numbers. The drive shaft must not yield up to 400 Newton meters. For whatever reason, we chose that value. And then the design process, finally, once we've sort of nailed down the actual numbers that we're trying to design the object to, we then consider pressures and priorities that are secondary to those. These are usually things like weight and cost. Those are usually the two big ones, particularly in the off-road buggies, motorsport and these sort of fields. And then there's also factors like manufacturability, which is important for small-scale production, like in a student team, but also extremely important for large-scale manufacturing once you become engineers out in the real world. So from here, you then usually take these definitions and these goals. You then design the object using whatever mathematics and engineering. That's the meaty bit in the middle. Newton's laws, your stress calculations, FEA, thermodynamics, bulk tables, whatever it takes to actually come up with a design. And I want to be specific here. As an engineer, you design the thing with the expectation it will meet the design goals. And that might seem like an obvious statement, like that's the whole point of it. But this is going to be really important later on when we come to validation. When we come to moving away from engineering, the idea that we're trying to design something that just won't break, to we're trying to design something to specifically do the job we're after. And that's sort of, I think, where ESI is trying to move with this validation event and try and move away from just buggies that don't break buggies that are really good at what they do and are well thought out. So just a few sort of recap things for the design process there. Alrighty, validation. So you're going to hear these 2 points quite a few times tonight, and they're really the two things we found ourselves repeating at last year's validation event. Validation is two core questions. The first one is summarized as, did you choose the right goals? So basically, do the requirements, so these requirements we're talking about back here, 800 RPM, 400 Newton meters, however you've defined the goals of the object, do they accurately describe the real world and the real world job that object will be doing? And this is, in some cases, seems quite simple. For example, your steering rack, it must travel 60 millimeters or whatever number you've chosen. That seems quite an easy number to come up with given your steering geometry. But suddenly designing other things like drive shafts, what diameter should they be? Knowing whether your design figure of say 400 Newton meters, knowing whether that's actually an accurate representation of what the part is going to be doing in the real world is quite difficult to define. It's quite difficult to ascertain. So that's one of the big questions that we're looking for in validation. Did you choose the right goals? How do you know that you've got the right goals? Where did you get those numbers from? And then also your safety factors. So it's one thing to say, I expect the drive shaft to be loaded to a maximum of 400 Newton meters, or I expect the suspension link to carry a maximum shock of 6 kilonewtons, or I expect the brake pressure to be a maximum of so many kilopascals. But then you put a safety factor on that, of course, just in case something went wrong. And we want to know, how did you come up with those safety factors? And specifically, how certain were you about the goals that you're going for? If you think your drive shaft's only ever going to see 400 Newton meters, is your safety factor then a relatively small safety factor because you're very confident, or is it a big safety factor because you're not very confident? You think it might be 400 or maybe 300 or 500, and there's a lot of wiggle room there, so you have a large safety factor. And of course, your safety factor also depends on what's at stake. So the safety factor that goes into rock climbing safety equipment is much bigger than the safety factor that goes into kitchen appliances, because a failure in the kitchen usually just means a mess, and a failure in safety or critical life-saving scenarios is obviously much more important. Okay, so another note on safety factor there. This is something which actually just popped up at the validation event last year, is you can apply the safety factor at different points in the process, or you might have several that are applied at different points in the process. So a safety factor on load, we think it's 400 Newton meters, we'll put a factor of 1.5 on that, just in case. Or is it on the stress? And in a lot of cases, those two vary proportionally. So if you have a safety factor on load, it's equivalent of putting that safety factor on stress. So that's not a problem. But in other places, they don't. There are some scenarios where, particularly in large deformation, like in springs or in suspension components, where a load safety factor doesn't implicitly carry across to the equivalent stress safety factor. So sometimes the stress safety factor is more important because, say, you're very confident about the load that's going to be on it, but the stress that the material can handle is more unknown. So the steel you might be using might have a yield stress of 350 megapascals, but the quality of the supply isn't so good, so you don't trust it to that. You only trust it to 200, and there's your safety factor and stress there. And also things like displacement, particularly for components designed around elastic displacement limitations. They have to be rigid to do their purpose, rather than yield failure limitations. They have to be rigid long before they have to survive an actual failure. That's where you put safety factors on those instead. And finally, material thickness. And this is the big point here. It's something that came up last year. We had a team that had a certain load for their drive shafts, a certain amount of torque. They then, I think they chose a safety factor of 2. That's fair enough, as long as they can explain it. And then they apply that safety factor of 2 to the diameter of their drive shaft. And those of you who've studied torsional stress within a cylinder would know that that causes a much bigger increase in the strength of the drive shaft. So where they thought they had a appropriate, not too big, not too small safety factor of 2, they actually had drive shafts that you could probably put in a truck. And they were carrying these things around the racetrack the whole time. They were too heavy. They probably cost more money, and they could have been smaller. So yeah, looking at where your safety factors come in and affect the actual mathematics of your component. All right, and question number 2, the other half of validation. Does your object actually meet the goals that you set for it? And I want to focus on the word meeting those goals. We're not trying to exceed those goals. If you exceed the goals, then you're carrying around wasted weight, wasted material. You might have made out of material that's much more expensive and stronger than it needs to be, because if your design goal was correct in the first place, it should be just good enough to meet it. And as an engineer, your job is to design these components to do a particular job, not to be good at a much bigger job that's unnecessary. Okay? And that's the big sort of focusing point of, one of the big focusing points of validation question number 2 there. And yeah, and just a second note to clarify on that one. We had a few people getting confused between the kind of validation we're after, which is, does your object do the thing you designed it to do? And instead we're validating manufacturing. Okay. Now, checking your manufacturing is an important thing. It's quality control, making sure that the parts you ordered or the parts you made look like what you want them to look like. But it's not the same as checking whether they do what you want them to do. If you measure it and it's 18 millimeters, is the same 18 millimeters you asked for, you validated your lathe, which is good, important, but you haven't validated the design. Okay, if you designed it to last up to 52 Newton meters and then fail at that point, and it fails around 52, that has validated your design, or it's at least validated the execution of your design. Whether the 52 is the right number or not, that's question 1. If it does 52 the way you want it, that's question 2. Okay, so alrighty. Validation in an ESI vehicle. So these 2 points I've just been talking about apply across just about every aspect of design engineering, from people who design watches, people who design aircraft undercarriage, people who design race cars, people who design machines that make tissue boxes. Every one of these has to follow design goals, hopefully meet them, not exceed them, because excessive achievement of these design goals is just expensive and wastage. And then we have to check those things. In ESI vehicle, how do you determine, or how do you validate the design target values that you've chosen for your vehicle? Excuse me for a second. So, a few different ways here. Well, I'll start by saying, of course, there are some that seem quite easy, and I'm not even going to get into those. If you can measure it easily, you should already be doing it. You should already know, how much rack travel you need, and how big your steering wheel needs to be, what's comfortable for your drivers, and this sort of thing. These ones are relatively easy to measure, but the ones that get tricky, and the ones where we see people guessing, that's the worst part. See people guessing is the ones that are difficult to measure, and that's the nature of the game. If it was easy, anyone would be doing it. So a few different ways of trying to get these difficult, elusive design targets. One option is you can derive them from other data sources. Sometimes this can be reasonably reliable, and sometimes people use it to make some really big jumps and assumptions. So an example here is you can easily measure the braking distance of your vehicle from a certain speed. You know how much it weighs, and you can measure the braking time. Could you use that to take a good stab at how much braking heat energy released? Yeah, you probably could. Within the sort of error bounds of the design, the kinetic energy of the vehicle, most of which gets turned into heat energy in the brakes. Okay, in terms of front-rear balance, it's a bit trickier, but you could sort of get a total heat energy reasonably reliably. But then when someone tries to use the braking distance data to determine their caliper mount loads, it starts getting more tricky because now your tyre to ground interaction is quite important. Any transient effects are quite important as the brakes get momentarily loaded and unloaded. And what else have we got? So your front rear, weight distribution, it also becomes very important. And so trying to determine your caliper mount loads from your braking distance has a lot more uncertainty in it. That doesn't necessarily mean you're not allowed to do it. You just have to account for those uncertainties. You have to design with those uncertainties in mind. If you can present a solid case of why you use those values, where the uncertainties are, how big they are, how you accounted for them, that's totally fine. The world of engineering is often full of cases like that where there's some big steps between the actual solid data and the numbers we're trying to achieve. But as long as you can account for all the bridges in the middle, you can still make it work. Okay, other options for getting these values. Measured and recorded directly. So what we're talking about there is telemetry, data logging, the fancy pants electronic stuff. Now, of course, this depends a lot on team budget, the team's electronics and data logging capabilities. Hint there, the more you can learn about telemetry and data logging, the more you're setting yourself up to succeed in the coming world of engineering, which should be obvious is becoming a lot more electronic. And it's a very good project to learn that on. But yeah, so difficulty and expense often get in the way of these things. And in some cases, it's actually impossible. So there are some things that you simply can't measure if you're trying to measure the torque load on a drive shaft. There are ways you could actually do it, potentially, that we'll discuss later. But using strain gauges is going to be really difficult because it's a rotating component. So sometimes there, the telemetry and data logging just aren't the right answer. Okay, sorry about that. Right, other options. So this is where we need to start getting a bit more creative. And I'll make a bit more of a point later on about how we can get into validation, what we say, on the cheap, on a budget. And two of the methods that I keep trying to suggest to students here, I've sort of summarized as what's called threshold apparatus. So compared to telemetry, which records a lot of detailed values over a long period of time, threshold apparatus is basically something which only tells you whether a value was reached or exceeded or not. And that may seem quite blunt. It'll tell you whether your drive shafts carried 300 Newton meters or not, but you can often do a few different tests at a few different loads with different thresholds. It might take a bit of setting up, but it can be done. And then those thresholds tell you that your drive shafts are always seeing, or are very often seeing 150 Newton meters, and then rarely seeing 300, but they never see 600. Okay, these are pretty broad ranges compared to the sort of detail you'd hope to get out of telemetry. But compared to absolute guessing, these are pretty concrete numbers. If you can say without guessing that the drive shaft never sees more than 600 Newton meters, that's a solid starting point to start designing your shafts around that value. So we'll break it up then into non-destructive. This is where we have components, and a lot of this is talking about replacement testing components. So before you actually get your final drive shaft, we're trying to measure how much load, say, last year's car has seen. And we basically come up with test components that slot in the place of your final components and are used to measure these things. So a type of non-destructive threshold apparatus might be something that undergoes elastic deformation and leads to contact. So for example, What can we think of here? If you're running an independent 3-link rear, so you've got the main swing arm coming back from the chassis to the wheel, and then 2 parallel, or mostly parallel links going sideways. And those 2 links are purely tension compression. I'd say an example there, if you could replace one of those tension compression links with something that's got a very stiff spring in it. And the spring can be replaced with other springs of different stiffness or different preload. So the link is preloaded to stay at its extended length until it sees a load of 300 newtons or 3 kilonewtons, whatever the figure may be. And then it compresses slightly and closes the contact. So there might be 2 faces. Say one of them's got ink on it, the other one doesn't. You load this thing into your vehicle, you go driving around, you come in, has the ink transferred across, has that component reached that threshold. Another example is something like modelling. If the ink doesn't work, something like modelling clay, which you squash against one side, and then after testing, if it's been squashed by the other side of the sort of 2-part elastic component, then you know that threshold has been exceeded. Now, to be honest, you don't even really need to tune the link to a particular load. You can just set it up with a certain spring that's about the right stiffness, and then go out testing, see what impacts happen, try a different spring, see what impacts happen, and then go back to your workshop and then apply the controlled loads to reproduce the behaviour you saw in the field, and that gives you your thresholds there. So another example there of contact is electrical, and this can actually still work reasonably well for a highly mobile component. If it's just a battery, a couple of wires that don't quite touch, and then they touch once a certain threshold has been reached, whether that's torque or compression or tension, or something more creative. I'm looking forward to seeing some creative solutions from students. And when the wires touch, so you have an LED in the circuit, the LED comes on. Now, excuse me, this obviously doesn't record data the way a data logger or telemetry does, or the way the ink or the modelling clay would, but it does give you live feedback. And pro tip, if you can go testing at night, of course, being careful not to run into anything in the darkness, you can watch out for these lights, and you can see whether your suspension leaks are being loaded. Is it being loaded over a jump? Is it being loaded in hard cornering? Is it being loaded under heavy acceleration or braking? Simply by watching out for the light to come on. As long as you've secured everything properly, it's not going to go flying off. You can actually do some pretty severe testing and get real sort of in the dirt field testing data that accurately represents the way you're going to be using this vehicle, just with a really simple setup like that. And again, okay, it's not super precise. It only gives you, however many increments you can get out of having different springs in this assembly, but it's something. It's a hell of a lot better than guessing. As for you as a design engineer, it's better than guessing. And when you're presenting it to either design judges or validation judges, it's also a lot better than guessing. So another example there, the non-destructive threshold apparatus might be thread tightening against a spring. And if we sort of break this down here, obviously a thread is a way of turning rotational motion into linear motion. So for example, here might be your drive shaft. If you have a 2-piece drive shaft, where they meet in the middle, they overlap so they can rotate independently, and then there might be a threaded connector that pushes down on a compression spring. And so this assembly will obviously take a certain amount of torque. The more torque you put into it, it will wind the thread down, compress the spring, until such a point where it can't do it. So where it hasn't got enough torque to keep compressing this spring. So you go testing, driving around, loading it up, you come in, it's loaded this thread to a certain point. You then basically take it off the car, take it to the workshop, take it apart, and then rewind it by hand with some sort of controlled torque. For example, lever arm and weights, until you've reached the same point that it was on the car, and voila, you know how much torque it saw, you know how much torque it experienced, in order to get to that point, and you've now got a good accurate measure of how much torque is going through there. And the nice thing about this is it's, as we'll mention a bit later with trying to theoretically calculate some values, is this actually captures things like impulse loading. The real sort of shock loadings that come through a system will usually be captured by something like this, which is data which is otherwise very difficult to capture. Okay, and then finally, some other ideas for determining the target values for a vehicle. So we've got other threshold apparatus which are destructive. So this is where you can't just simply reset the assembly with modeling clay or ink or unwinding the thread on the spring, but where something actually gets broken, hopefully in a controlled and safe manner. No one likes to accidentally break things on the car, but if you can set something up to break at a pre-defined or pre-known load, then you can tell whether that threshold has been reached. So for example there, for going back to drive shaft torque, if once again you have a two-piece drive shaft, say an outer sleeve which goes over an inner core, so an outer sleeve from one end of the drive shaft and an inner core from the other end. Where they overlap, you have a pin going perpendicular through the two of them, and obviously that pin is loaded in shear as the drive shaft conducts torque. And for different size pins, it will eventually shear off at a certain torque level. If you can control if you can put different size pins in there, and then once again measure them in the workshop, get an idea of what sort of torque they fail at, and then go testing, see what sort of failures you see from these shear pins. Obviously, once it's failed, you lose drive to that wheel, pull over, get someone to knock the stubs of the pin out, put a new one in, and go again, maybe a new one with a different size. And so that's a destructive test with a threshold apparatus, so you can actually get reasonably good consistent values for how much torque is going through that component. And then the final one there, progressive controlled failure at increasing load, is basically a long way of saying having many different pins of different sizes all in there at once, and then as the load increases it'll shear the light ones until eventually it reaches one which it can't shear. Obviously this is much more difficult to manufacture, and there's some other sort of things to bear in mind there about impulse loading and failure, friction, this kind of thing. But it's basically just a more expensive way of doing that more quickly. So yes, ideas for coming up with these design target values in places that are normally quite difficult to measure. And of course, these are all just general concepts. I've used examples of drive shafts and suspension links because they're quite easy to visualize. But all over your cars, you'll find places where you go to design a component, you say, how much force is it carrying? And you go, not sure. That's going to be difficult. I'm not sure how to figure that out. I know it carries about this much because it's connected to these other components, but I don't really know what to design around. These are the places to start getting creative. These are the places where design judges love to see your innovative ideas, that we came up with this apparatus and it had this measurement and it had this pin and this spring and whatever, however you do it. It always looks good that you can come up with ways of measuring things that other teams are just guessing at. If you can go up to another team and go, I know pretty well what value goes into there, then you're already one step ahead of them in that sense. So validation question 1. Validation question 2. All right, question 2, real testing of a component. So you got your values, you used your stress calculations and your FEA and all your cool fun toys. You design a component, you get it made. We need to know, does it do and only do what you wanted it to do, what you intended it to do? So how do we test these things? Some components are lucky enough we can just test them in a workshop. Coming back to our example of a drive shaft under torsion, it's actually quite easy to test, and it's surprising how many teams don't use this as a validation option. It's so simple. You just clamp down. You get a bench, nice sturdy bench. Clamp down one end. Okay, you might need something like a CV joint or something that's splined to take the torque you're about to put on it. But we clamp that down to a bench. At the other end, we support it so it can't move, but it can rotate, of course. We fit a lever arm to it, and then a lever arm of known length. And we hang weights off it, whether it's your dumbbells or your gym weights or sandbags or buckets of water, anything you have a good, accurate measure of the weight. Hang that off there, force, distance, torque, until it breaks. Just break it, you've tested it, beautiful. If you want to be a bit more sophisticated, and I hope you do, you can use this as a learning exercise. Okay, to validate the component, we just need to know, did it fail when I expected it to? That's sort of the core question. But you can use this as a learning exercise to teach you more about how your drive shaft is behaving at the extreme end of its usage range by using a protractor to measure the amount of angle change in the drive shaft. So of course it's going to twist a bit elastically as you increase the weight. Of course, record the weight and compare it to the angle. And if you record enough data points, you can compare these and come up with rather than a force displacement curve, we have a torque rotation curve. And this will tell you really useful things about the elastic range, the plastic deformation range, what happens near rupture. And again, this is great data that you can bring to either a design event or a validation event as appropriate. Other components that we can't just workshop test by themselves because they rely on surrounding components to load them accurately. So a good example of this is chassis stiffness. Effectively with the chassis, you can just grab it at the back and grab it at the front, twist it, but this is not how the chassis gets twisted in real-world usage. In the real world, the torsional stiffness we're after is the hub-to-hub stiffness. This is effectively, say we replace our shock absorbers with rigid links, and then fix the rear two hubs, take the wheels off, fix the rear two hubs to the ground, and then grab the front two hubs, lift one, drop the other. How much twisting torque do we apply to it to get certain rotational torques? To get certain angular displacement, sorry. I'm a bit sick at the moment. And in order to do this, we need to have these suspension components attached, the links, A-arms, uprights, whatever else you've got in there. So yeah, some components we need to test in the workshop, but with other components attached. And while we're on the chassis, I want to make a suggestion here of, once again, you can just get a design figure of your torsional stiffness and see if that was what you expected it to be. But you could also learn a lot from this, and complex components often have a lot to tell you if you listen to them right. An example here is that instead of just recording the angular rotation at the front hubs and comparing it to the torque you've applied, why don't you also record angular rotation at several stages down the length of the chassis, and then see where the torsional flexibility is within your chassis. Okay, it might not help you to change this year's chassis, but it will tell you really important things about your design and how you can change it for next year. So another way you can do that, one way you can do this with the chassis is just basically take something like a broom handle, basically a long, rigid length of wood or steel or something, basically strap it rigidly across the chassis. So one at the very nose, you've already got one across the front uprights, the front hubs. So put another one at the front of the driver's window, say where the pillars come down to the side rails. Another one at the back of the driver's compartment, across where his back is, and then another one at the very rear of the chassis. And this will tell you that even though across the whole hub-to-hub stiffness it's 5 degrees at this certain torsional load, it'll tell you that of those 5 degrees, 3 degrees are happening in the front suspension, so that's obviously very flexible. Half a degree is happening in the front third of the chassis. Another 1 degree is happening in the middle of the chassis, and half degree is happening down the rear. And this sort of tells you where you can change your chassis in future to affect its torsional stiffness in different ways. So the point there being, while you're doing this real-world testing of your components, don't just think, how can I answer the question of does it do what I designed it to do? Okay, you need to answer that. But while you're at it, think, is there anything else we can learn from this? Is there anything else about this component that I would like to know? And maybe I could figure out alongside the testing I have to do to figure out whether it just does what I want it to do. So some things we can't test in the workshop, and we want to go field testing. I want to first make the point here that it should be very difficult to go field testing your components in a way which is meaningful for validation. I know a lot of teams a lot of teams go all through the process of building their car, and they go field testing, and then it doesn't break, and they say it's been validated, and that's really missing the point of validation. Because if you're field testing and you don't break anything, it doesn't mean that it's a valid design. Validation isn't showing that the design doesn't break, it's showing that it breaks when you want it to. It's showing that it does what you want it to do. Because you could go testing an army tank, and of course it wouldn't break going around the track, but it's still a bit heavy, and you could maybe have made a lighter vehicle that broke when you wanted it to, and not at just ridiculously high values. Apart from that, field testing can be quite dangerous, particularly the whole point of this is to break things, is that you expect that such and such will break at a load of 600 newtons, so let's go out and put 600 newtons on it and see what happens, and suddenly it breaks and people get hurt or get in trouble. So it can be dangerous, field testing, and yeah, like I said, safety factor should mean that if you design the component correctly in the first place, it should be almost impossible to destructively field test it. We should hope so. There are some components which stand out from this. So for example, tyres. It can be safe and in fact it's essential to do your tyre validation or tyre testing in the field. It doesn't work very well in the workshop. Aside from having really expensive machinery, even then, still not great. Field testing is good for tyres. And it's reasonably safe because once you've exceeded the design limitations of the tyres, you might get a flat tyre, which is usually okay, or you've just skid, so it's not a problem. But yeah, so remembering that field testing often is very limited in validation. In validation, we're trying to be quite scientific. We want to take away extraneous factors and influences and just see if it does what we thought it would do. Alrighty, validation question 1, validation question 2. So those are our definitions. Now I'll just quickly spin through some examples, and would you look at that, it's our old friend, the drive shaft. So we'll go through 5 examples here of common ESR components, just to sort of step through the process and the mindset we're trying to get from students in validation events. So drive shaft torque, ways you could come up with your value. Well, for one, you could just design it to be stronger than something else. Your drive shaft is basically one great big long chain of torque and speed and ratio, give or take. And if the drive shaft is not the weakest component, then maybe that's pretty good enough. That does the job. However, now we need that doesn't agree very well with a lot of other design philosophies. For example, CV joints are usually quite expensive. And if you can get cheap source of drive shafts, it's much better to have them break before the CV joints. They're often easier to change as well. So yeah, that's not a great strategy. Other strategy, calculated from the vehicle mass, acceleration, engine torque. This is a common strategy we saw last year, and it has huge room for error. It's a good minimum starting point. You can get a good idea of how much load is going to be on the drive shaft just to get the vehicle racing. And if you design it for less than that, then it's almost certainly going to break. But you miss huge amounts of impact load, of sharp shock load. And the example we kept using was when the vehicle goes over a jump or off a drop-off. The vehicle goes off the ground for maybe a second, half second or so. And the driver's doing his job, and he's got his foot flat on the floor, because that's his main thing he has to do. And the engine revs up, and the wheels speed up, and then suddenly they hit the ground, and bang. The wheels are going too fast, the vehicle's going too slow, the ground's coming up too quickly. No one wants to let go. And often in off-road racing, the higher level off-road racing we see in America and Baja, in the Baja 1000, drive shafts are usually the thing that fails. So yes, you miss out on huge amounts of transient effects when you just base it on steady state or say steady acceleration loading like that. Okay, option number 3, strain gauges on a moving subject. Good luck, all the best. I would love to see it if someone can do it. Other than that, our controlled failure drive shafts we were talking about earlier. So be creative, come up with something like a shear pin or a torsional spring, some sort of sensor like that, threshold sensor on the drive shaft. And yes, I've been very impressed at validation that people can come up with actual real drive shaft torques, or at least a range of torques. We know it's between 300 and 426, because that's where our pin did not fail. All right. Safety factor. You know how much torque it's actually going to see. What's the safety factor do you put on it? How confident is your design figure? So if you got it from theoretical calculations, how confident is that theory? How confident are the numbers that feed into that? If you got your figure from experimental testing, what was the statistical distribution of that? And this is where I actually would love to see some real nitty-gritty statistics. I want to see means and standard deviations, showing that 60% of your failures occurred within this range, 90% occurred within this range, and therefore the expectation is that the probability of a failure above so many Newton meters is this percent, which we have concluded is an acceptably low failure. This is great things to see if you can bring that sort of a statistical analysis of your experimentation. Okay, of course, the safety factor, is it a factor of torque or stress or diameter? That's the thing I was talking about earlier, where increasing the diameter massively increases the strength of the shaft beyond what we would normally expect from a stress or a loading safety factor. And of course, when you're determining your safety factor, what's the consequences of failure? Is someone going to die if this thing fails? No, probably not. But you might be knocked out of endurance, or you might fail one of the earlier events, acceleration. You might be knocked out of endurance either permanently or for 20 minutes, an hour. So you generally don't want this thing to happen, this thing to fail. But because you don't have a life riding on it, like you would with the rock climbing safety gear, you probably also don't need a 15-to-1 safety factor either. And then finally, real-world testing. Do your actual drive shafts perform the way you designed them to? Basically step through that just before of how to measure that, or how I would measure that. Of course, I'd love to see students come up with other ways of doing it, especially if they're cheaper and easier. That's the whole idea. So, do they fail at the torque you aim for? If you tested several, what's the statistical spread? How do those failures, are they consistent? Are they very uncertain? How is that spread out? Next example, brake pedal strength. Step 1, question 1, determining your design values. How did you come up with these values, and how do you know they accurately represent the real world job this thing has to do? We can come up with theoretical values based on brake pressure and master cylinder forces. You can actually measure brake pressure and get actual master cylinder forces if possible. You can also, for example, do workshop testing with the driver pushing on the pedal. They're the one that's going to be doing it in real life, so get them to jump in the car and stomp their heart out. However, you've got human variation factor. So obviously we're still trying to measure this based on a load cell or putting a set of bathroom scales in front of a driver and getting them to go nuts. But you get human variation factor. Now, some people will stomp a lot harder on bathroom scales than they will on the race car they've spent all year building. But on the flip side, some people will be gentle on their precious race car in a workshop, but then when a slow car pulls out in front of them, they're not so gentle, and they stomp on brake pedals like crazy. I think Formula One drivers sometimes put something around 150 to 200 kilos of force on their brake pedals, so yes, keep it in mind. All right, safety factor, how did you determine it? your theoretical values. Are you confident in your brake pressures, either your theoretical or your measured pressures, and how well that transfers across to the force on the pedal and therefore the strength of the pedal? If you did experiments, how consistent were your drivers? How consistent was even one driver? Did they always put out the same force, or did they vary greatly? How confident are you that you can cover all the different forces that all the different drivers have put on it? And your factor of safety, are you multiplying the force by a safety factor, or the stress, or pedal deformation? Are you more worried about the pedal elastically bending out of the way and not doing what it should be doing? And of course, your consequences of pedal failure are somewhat more dire than consequences of a drive shaft failure. It's harder to replace the brake pedal, should your car be lucky enough to make it back to the pits. Odds are that it won't be, and you might run into a tree or a pile of dirt, or worse still, a spectator, and then you're in really dire straits. So your safety factor should reflect that. And finally, question number 2 from validation: does your pedal actually do what you designed it to do? Does it fail at the load you aim for? It should be reasonably straightforward to test in your workshop. Set up something nice and rigid, measure how much force is coming through it, or how much weight you can hang from this pedal if you turn it sideways, until it fails. Example number 3, steering column. I'll just give an example here of a straight steering column. I know it's very simplified compared to what we see in a lot of cars, but just using it as an example for explanation. Say it's a straight steering column. It's supported by a couple of bearings or bushings, and obviously you've got the steering wheel mounted at one end. Now in this case, it sort of differs from the ones we've just seen, which are a nice simple bending load, or a nice simple torsional load. Here we've got torque and bending at the same time, and we've also got to consider whether we're concerned about actual yielding failure, so the driver putting too much steering input in and twisting the shaft, or the driver holding onto the steering wheel, say during a crash and the shaft bends, or are we concerned about elastic failure, because that's almost a contradiction, but poor elastic performance because it's not rigid enough. So the driver's holding onto this thing, and it's no good if it's like a piece of spaghetti and it's trying to steer, and the steering wheel's like elastically flopping all over the car. Okay, it's not braking, sure, but it's no use to him if it's bending too much. So how do we get our input load? So obviously it's validation question 1. Determining your design values. How do you get these things? Strain gauge is good. We can put strain gauges on this because it's not rotating very quickly like a drive shaft, but of course that's quite expensive. Other options: the driver's maximum holding ability. Put him in the car, get him to hold onto it, and start putting known torque on it, like with a torque wrench or a lever and again a set of scales, until the driver can't hold anymore and has to let go. This is a reasonably good approximation, but well, it might be. I want to know whether you can prove whether it's a good approximation or not. But you can fail to represent the impulse loads on this. When the driver hits a bump and suddenly, if you've included a lovely amount of scrub in your steering geometry, it sees a massive impulse load. Other things here, like with our previous torsion examples, we could use a shear pin test. And we can sort of see that in the illustration here. The pin goes across the coupling into another piece of shaft. Hopefully it's obvious to everyone that this is really dangerous, because basically once you've reached your nice interesting data point and you know how much torque it takes to break the pin, then you've then lost control of the vehicle. So I hope I never see anyone doing that. Or what about an alternative of a static friction collar? So a collar that clamps down 2 adjacent pieces of shaft, and once you put enough torque into it, it will slip slightly, but once the torque eases off, it returns to being a rigid coupling. It's a lot safer, but still lets you then take that coupling over to a testing workshop and apply known torque until it slips, and voila, you know how much torque was applied to the steering column. We'll just keep spinning on quickly. Excuse me for a second. joys of being sick. Safety factor. Yep, so again, how confident are you in your theoretical values? Here we seem to mostly be running off experimental values for this one. So in which case, how are those experimental values distributed? How confident are you? What sort of statistical confidence and probability do those values give you? And again, factor of torque, is it actually a factor of stress, a factor of diameter, a factor of deformation in this case? Please list where you put the safety factor in and why there, why that much. Consequences of a column failure. Obviously, when you're racing and the steering column fails, you're out of the race, you've possibly also lost control and done a lot of damage. So that's a very severe consequences. But also the consequences of poor stiffness. So if it's, like I said before, it's the driver is finding the vehicle difficult to control at speed because it's not rigid enough. What are the consequences of that? Well, you're not out of the race, but it might make the next 4 hours of endurance very unpleasant. It may also reduce your driving performance. The driver can't go as quickly because the vehicle's hard to control. So taking all these things into account when looking at your safety factor. And finally, validation question 2. Does your actual column perform the way you designed it to? Does it fail in the conditions you aimed for? If you aim for it to fail at certain torque loads or bending loads, then obviously you also need to consider combined loading. The stress distributions inside a cylinder under torque and bending are non-trivial. So it's a good chance to go and become familiar with those if you're the one doing this component, and see what sort of combinations of those are likely to affect the failure of the component. And once again, failure in terms of actual yielding, or also failure in terms of excessive elastic deformation. Example 4, the width of the gears. This might sound like a bit of an abstract example, but often when students are designing these gears, the width chosen is kind of arbitrary, or it seems arbitrary. Excuse me for just a second. 2 seconds hold. Just got some technical. No, we're all good. Okay, width of the gears. Okay, so again, I chose this example because it combines 2 different failure modes: the wear rate of the gears, and then also the spontaneous failure, which is breaking a tooth off, basically, or breaking the gear itself. And obviously both of these present issues to an ESI vehicle, but they present the issues in very different ways, and they come from very different design strategies, or they result from different sort of design choices. Anyway, before we get to that, of course, we need to know how much torque they're carrying in the first place. How do you calculate these things? So, torque load. In the past, when we've talking about torque, we talk about maybe having a shear pin, and in theory that sort of works for these gears. You could make gears with an extended hub where all the torque is carried by a shear pin, and when the shear pin fails, you know that the certain measured amount of torque has been exceeded, but that becomes very difficult inside a gearbox. It's completely different from on a drive shaft where you can just stop the vehicle, punch it out, put you on, and away you go. You don't want to be emptying the oil out, taking the gearbox apart, dismounting it from the vehicle, changing the pin, putting it all back together again. You waste huge amounts of time. So maybe a slip hub. At least then you don't need to actually take the gears off the shaft, but you're still taking the thing apart. So that's that friction hub we were talking about earlier, where a certain precise amount of friction holds it onto the shaft, and then we can measure afterwards what sort of clamping levels led to what amounts of torque, and therefore we can see when it was slipping in operation. Excuse me for a minute. Okay, but again, that's inconvenient. We've got to keep taking the gearbox in and out over and over again. But as I said before, a lot of your drive shaft components you can sort of think of as all links in one big chain that starts at your crankshaft and ends at your tyres. And so if you've gone and done the research on how much load your drive shafts are actually taking, then you can probably make some reasonable assumptions about what loads your gears are taking. And again, don't take my word that these are reasonable assumptions. I want you to explain why these are reasonable, how reasonable they are, how much you trust them, why you trust them. That's your job. So that's sort of a two birds with one stone kind of thing, where if you can do research in one component and then look at what other components does this information tell me about. Or the other option here, like we say, is something like a few component, which is a topic or that concept we started on earlier, where you don't have to be the strongest component, you just have to not be the weakest. If you know that something else is going to fail at a lower load, then you just design it to be substantially stronger than that. And again, this is not a great strategy because it just ends up resulting in extra weight, extra size for your components. But in something like this, where we're having a lot of trouble coming up with a good design value for it, we don't want to guess because we're actual engineers and we don't guess these things. It's hard to come up with value. And so we can resort to other more wasteful strategies, such as we make sure it's stronger than the other component further down the drive line. Okay, the amount of torque that's going on it. Now, while we're also choosing our design values, discovering our design values, how much torque is possibly going through these gears. The other design values include how much wear is allowable. So the gears are going to wear over time. They'll lose shavings off their surface. Eventually they'll wear down to be, well, that's the question. How much can they wear down before you're not happy with their performance? Is it going to change the mesh? Is it going to start making too much noise? It's probably not a problem in motorsport, but it can become a big problem in something like an air conditioning system. Is the wear on the gears going to result in more backlash, which then causes more shock loading through other components? Is the wear of the gears going to release a lot of contaminants? And this can be a problem in other fields of engineering. So that's another question you need to answer. And then, of course, also the amount of fatigue cycles that you're happy with these things to see. Because often one of the big failure modes in gears is just fatigue. They're not actually broken off by one particular heavy impact. They actually just fatigue over time. So how many fatigue cycles are you designing this thing for? How long do you expect to use these gears? They're going to last for one season, and that consists of so many kilometers, and those kilometers consist of so many gear rotations, plus racing, plus safety factor, etc., etc. Speaking of safety factor, once again, the same old things. If you use theoretical values, how confident are you in the theory? If you use experimental values, how confident are you how much statistical spread do you have in your experimental values? Are you putting a factor of safety on the amount of torque? Double 400 Newton meters up to 800 Newton meters. Are you putting a factor of safety on the stress because you don't trust the material? On the wear rate, because whatever you use to calculate wear rate, I'll confess I'm not that very familiar with the mechanics of wear on gears, but I have a lot of confidence. There are many books out there written about it. It's a great opportunity for you to learn about it. Are you going to put if you don't have much confidence in those wear rate calculations, is that where you put your safety factor? Or is it the fatigue cycles? And of course, the safety factor in fatigue cycles gets very tricky because fatigue is extremely non-linear. Have you ever seen your what's known as an SN graph showing fatigue life? It's extremely non-linear, and changing from a safety factor of 2 to safety factor of 3 can have massive effects on either the allowable stress in your components or the allowable number of cycles you can put it through. And of course, the consequences of spontaneous failure, you break a tooth off the gear, you're probably out of the race, and it's probably too hard for you to fix it in the pits. What about consequences of excessive wear? Is that something that you can deal with during the race? Can you readjust your racing strategy to allow for excessive wear? I mean, perhaps the ideal scenario is that, well, put it this way, if you get to the end of the racing season and your gears look brand new, then you had way too much gear. Okay? They were way too strong, they had way too much wear life, and you could have gotten away with gears that were much, much narrower, and then would have been lighter and cheaper and all these other things. So a good outcome for this is that your gear should be wearing just to the point that you want, which of course is another way of saying validation question number 2. Does your component actually perform the way you want it to? Of course, you do physical testing of wear rate by measuring the material wear of the gears periodically, and of course recording how many kilometers or rotations or whatever you want to call it occur between each measurement interval, and hopefully from this you can actually get good data showing the gears wearing over time, and if your validation has a good outcome, it will show that they're wearing at about the rate that you, the rate that you expected them to. Okay, the other thing, of course, that we want to check for real-world failure is the spontaneous failure of the gears. How much torque can you put in before you actually rip a tooth off? And unfortunately, this is probably something you can perform outside the gearbox with necessary safety precautions in place, so no one gets hit by a flying gear tooth. But it's something you can do in a workshop. And yeah, and again, it's great validation to bring to the event. Okay, final example. All right, just one for the electric teams there. The cable size of the electric cable feeding your motors. And I'll say, of course, that I'm not an electrical engineer. I'm sure there are people who know a lot more about this than I do, but I'm sure we can all learn from this example about how the same principles of validation can be applied to many, many different components on the car. So, validation question 1, here we go again, determining your design values. You can calculate them theoretically from your motor capacities or your inverter output. You can also calculate them theoretically from how long it takes your accumulator or your battery to be emptied. But of course, with that, you miss things like the transient peaks, the spikes in the load, and you're just assuming a lower average load. You can data log it from real-world testing if you've got the facilities and the resources to do that. That's fantastic. That's very accurate and very impressive. Way down the simpler end, you can use, again, our threshold testing components. For example, with a fuse, an actual fuse this time, which obviously just tells you when what sort of maximum current you've reached. Okay, when you're just choosing your design values, you also need to choose what cable temperature is allowed. We want to choose cables that we can put the right amount of current through without them overheating and melting and catching fire and doing all sorts of nasty things. But what is that temperature that's going to be allowed? What are we prepared to live with? On that, how do you determine your safety factor? Same old thing, how confident are you in theoretical values, or what's the statistical distribution of your experimental values? And what's at stake if a wire overheats? Sometimes it might just be that it goes pop and your car stops. Again, that's not a great outcome in any sort of racing event, but it's relatively low danger, let's say. Or if it's in the wrong place, your wire overheats, causes a fire. If you've got lithium batteries, then a fire in there causes problems for lots of people in the local suburb with wonderful noxious gases. So yes, a lot of variation in what's at stake for designing electric wire size. And hopefully your safety factor reflects those consequences. And of course, finally, validation question 2. Does the design selection you made actually perform the way you expected it to? We can do physical testing, see if it overheats at the design current. We can also go testing it on the car. Field testing may be very dangerous. Like I said before, hopefully if you've designed it right, field testing is of no use to you because you'd never reach those failure levels. And it can also be extremely dangerous because things can catch fire. Hopefully that should be obvious to everyone. And yeah, okay. It's the end of the examples. And now I've got a couple of slides about the teams doing validation on a budget. You just have to excuse me for a second. Alrighty, back in it. Validation on a budget. Oh, we don't have the resources to test that. Okay, no one has the resources to test everything, but you need to be creative. As hopefully I've shown in all the examples we've been through so far and all the little side tangents and ideas, you can be pretty creative and come up with some at least useful numbers. I won't be the one to say that the numbers you come up with are superbly accurate and you can design your entire vehicle around them, and you can completely base all of your designs off them. But they're better than guessing. And sometimes I feel like that should be the mantra of engineering departments at universities. Like engineering, it's better than guessing. Because a lot of the time, that's all it boils down to. People have been designing things for centuries or millennia by guessing these things. And what engineering does, it comes along and doesn't guess. It actually measures them. So, don't guess, try and measure things. Of course, they're going to be difficult. If there was an easy way to measure these things, like drive shaft torque, we would already have a nice ruler that does it for us. We don't. You have to be creative. Okay, you're the engineers, and when you graduate and go out into the real world, the skills you've acquired in trying to measure the unmeasurable are really going to be helpful when you've got a job and for your employer, because you might be surprised to find yourself one day standing around a project and everyone's scratching their heads going, how on earth are we going to measure this? How are we going to get accurate numbers? And you can be the one that puts your hand up and says, this is just like that time we had to measure something similar on the university race car team. And here's how we did it. Here's the problems we face. And I'd recommend doing this or that and not doing this. And suddenly you've brought a solution that no one else had because they hadn't had to face this problem when designing a race car. So be creative. As an engineer, it's your job to solve these difficult problems. And the best way I've sort of found of trying to address these is to break the problem down into its fundamental pieces. Go all simple units on this thing. Things you can actually measure: distance, mass, speed. Okay, you don't have a torque sensor and a bending stress sensor for a steering shaft, but you've got a basic set of scales, a spring balance, call it, that you can use to measure force. You've got a set of bathroom scales you can use to measure how much force someone can push with their foot. You can create a known amount of torque with a lever arm and buckets of water, accurately measured buckets of water. And you can control it very easily. It's repeatable. And there's so much you can do with just simple things. And particularly just trying to focus on one validation aspect at a time. See, a lot of your components are quite complicated. For example, a suspension upright does a lot of jobs at once. It's very tricky. Focus on just validating one thing at a time. Okay, caveat there, you do have to consider combined loads, but you can validate some reasonably fundamental things about your design by just focusing on one thing at a time. And yeah, like I said, they're using the displacement of a spring to determine force, or the rotation of a spring to determine torque, or find a way of converting one aspect of your design you're trying to measure. Convert it from something that's difficult to measure into something that's much easier to measure. Excuse me for a second. Okay. Another thing, they're low accuracy. So yeah, a lot of the things I mentioned so far are pretty inaccurate. They're not going to win any prizes with the International Standards of Accurate Measuring Committee. But like I said earlier, they're better than guessing. They're a lot better than guessing. And even if they give you a wide range of numbers, they give you some reasonable certainty that it is at least within that range, and it's not way outside that range. So the low accuracy can be acceptable as long as the rest of your validation and your design process and your explanation of all this takes into account however much uncertainty you think is there. And finally, be scientific. And particularly beware of human bias. I've been on a university motorsport team. I know just how much, as a suspension and chassis designer, and then the chief engineer, I know how much you want this thing to work and how hard it is to stand back and say, let's see if this thing does what we expect it to do, because you just want it to do what you expect it to do. But beware of human bias. Try and be scientific about it. All right, finally, the actual validation event at ESR. Here's just a few feedback points from last year. Point number one, please put your team name or your car number on the report. We had reports last year that were completely anonymous, which is useless. It's so much wasted work when a report comes in that we have no idea who it's come from. It's not really good enough for ESI. It's definitely not good enough in the professional engineering world to miss out those kind of details. So step number one, make sure you put that on there, on the report. When it comes to the actual validation event, something we found ourselves telling teams was that they would try and jump into a 5 or 10 minute explanation of what the component does. This is the drive shaft. It can get torque from here to here. Here it is on our car. Here's some more examples from other cars. You don't need any of that. Get straight to the point. You might want to do that in a design event. That's up to you. But in the validation, we asked you to do this particular component. We know what the component does. Just jump straight down to it. Unless your component does something really special that we might not have thought of. For example, one team had drive shafts that were also suspension links. They had many other loads that were on the drive shaft they had to take into account. Let us know about things like that, but otherwise, get straight down to it. We're there to see that you answered the two questions. How did you determine the real target values, including determining your safety factors? And then how did you real world test your component to see if it did what you aimed it to do? Okay. Another thing, acknowledge any shortcomings in your method. It's much better for you to tell us these are the inaccuracies and the shortcomings, and we know it's wrong here, but here's why it's still acceptable. It's much better for you to tell us that than for us to tell you, because then we get to pick it apart. If you can come out and say, here's our apparatus and our method, we know it's inaccurate because we didn't include this, however, we've included another factor that compensates for that. That's all great. That's what we want to hear. You can mention methods which were tried but abandoned. That's a good example of your learning process. We had one team last year that had a method for measuring the angular displacement, the rotation of their chassis during torsional testing. And they said, we started with this method, however, we found it to be imprecise. Here's some examples of numbers we came up with. Look how imprecise they are. We go, oh yes, those are imprecise. Instead, we tried this other method and it worked better. It was more expensive, but that's really good. That's good stuff to hear. Don't spend too long talking about things that went dud, but it's good for us to see that you took cost into account. You didn't just go straight to the most expensive method, it worked, tick box, done. Okay, you got the result, good. But if you can say, yeah, we tried this, didn't work, we tried this, we thought about this, we put thought into it. That's mainly what we want to see. And very finally, if you can bring failed components, they make good props, as long as you can explain them. So if you come into the validation event itself and you've done your drive shafts, you say, here are our broken drive shafts. The validation judges love to grab hold of them. They're nice and shiny. They can look at them and see where they broke and go, oh yes, this is where they broke. That sort of shows that you did do destructive testing, but it's also much better if you can then say, and look at where it broke. Here is the such and such a failure point, and here is why we think it failed at that point, and be able to explain the props a bit is also really good. But in general, if you can bring failed or broken or bent components, or even components, okay, so you did validation and turned out your component did not fail when you expected. Instead, it failed at 1.5 times higher. There's a fair bit of error, to be honest. But if you can still bring that in and say, hey, here's where we tested it, here's the impact marks from our testing machine or whatever, that's still great things to hear. So, alrighty. We did get a few questions. Unfortunately, a lot of them were just really specific components. How do I validate this or this or this or this? That's your opportunity to be creative, to try and test these things out. But sorry, I'm just trying to remember now. 2 questions we did have. Someone's saying, how precise do I have to, or do we have to be for our values? Again, this is where we come back to statistics, fun math statistics. But it becomes really important because what statistics do is they turn uncertainty, they turn individual data points into confidence or not confidence. And really, as an engineer, you can never rule out, or you can rarely rule out certain things entirely, but you can express them as an extremely low probability that we are happy to live with. Back to the question of how precise do I have to be? As I said before, as long as you take into account where your imprecisions are coming from, that's a great start. If you can then express your imprecisions in terms of we're imprecise to this degree across these ranges in a statistical sense, a probability sense, this means that a failure of this type has a 1% probability, and a failure of this other type has a 0.1% probability, and we deem those to be acceptable values. That's how precise you need to be. I suppose that's a pretty roundabout answer, but the answer to how precise you need to be is just precise enough that you can have confidence that it is sufficiently unlikely to do what you don't want to do. Again, that's a very roundabout explanation, but I hope someone can sort of see what I'm trying to get at there. The other question we're going to answer. Just look this up. Sorry, just have to bear with me for a second as we try and bring this up. Joys of technology. Okay. Shock absorbers. Yes, how could I forget that? Sorry for that. Wait. Shock absorber force. How to validate, how to measure the shock absorber force. This is very tricky. I mean, sure, you can have failure threshold ones by putting progressively weaker bolts in there, but a failed shock bolt is expensive in so many ways. So we won't really look into that option. How can you measure it on the fly? Honestly, I'm still going to say your best option there is to try and measure your suspension positions. Basically measure how long the shock absorber is across many different points in time. And not just how long it is, but how fast it's moving. Obviously, that's kind of the point of the shock absorber. And then from there, calculate the forces that are coming out of it, which then leads into the question, how do I know what forces are coming out of my shock based on how long it is and how fast it's moving? And what we're talking about there is a shock dynamometer. For those of you not familiar with it, go and Google it. It's very interesting. I advise you to read as much as you possibly can about that. It's a great topic and a lot of great things to learn there. They're also very expensive and quite rare, so how can you do it on the cheap? Well, boil it back down to, we're trying to take our shock. We want to, say, build an apparatus that will compress it across a certain length at a certain speed, or at least, even if we can't directly control what that length and speed is, we want to be able to know what they were after the test so that we can then start piecing together data points. So to compress a shock, you really just need, I'm trying to put it, a fixed point and a lever to try and squash the shock down. Whether you make this frame out of steel or you bolt it to the ground or what, it doesn't really matter. But if you can then drop weights on it, now you know the potential energy of the weight where it started, so therefore you have a good idea of the kinetic energy of this falling weight as it hits the apparatus, the shock, however you've set it up. It then transfers that energy to the shock absorber, effectively using the shock absorber as a suspension component for dropping heavy things in your workshop. Now, how do you then measure those things? You measure the similar ways that you would measure them on the car with linear potentiometers or rotary potentiometers on your suspension components. Yes, and then looking at speed that it's moving at over time. If you can't get into the data logging telemetry potentiometer game, you can, for example, put a marked, a ruled backdrop behind your apparatus and then film it. And of course, there are lots of sources of error here that you need to keep in mind, but if you can work your way around those, you can record at 25 frames per second. If you've got a sweet new iPhone, I think you can do 120 or 240 frames per second. And that's actually a reasonably good data rate for the sort of speeds and distances we're talking about here. You can record it on the camera, look back over the footage afterwards, look at what basically going through it frame by frame. Okay, that's tedious, but sometimes that's the price you pay for not paying the price of telemetry and data logging sensors. And yes, record it. You can have a look back over it frame by frame. You can see how long the shock was, put all those data points together, look at how it changed from one frame to the next, and now you've got velocity, or at least an approximation of it. And you can start to then piece together how that known kinetic energy was absorbed over a certain length and a certain amount of time and certain velocities. And you can actually start to build up data about your shock absorber of you should have a good idea of its spring stiffness. That's much easier to measure. But this damper property of how does it turn velocity into force like a good damper should at different velocities, at different displacements. So yeah, that's my best shot at the El Cheapo shock dynamometer. But yeah, again, it just comes down to being creative, setting realistic goals of how much you're trying to measure. Okay, 1,000 data points per second at 0.5 millimeter increments might be great, but if you can measure at 2 millimeter increments 20 times a second, it's still way better than guessing. Always comes back down to that. So a lot of validation comes down to is how good was your not guessing to start with, and did your not guessing, did your component eventually do what you originally not guessed it to do? So we'll finish on that great example of technical language. And yeah, I think that's pretty good. We'll leave it there. Thanks very much for listening, and we'll catch you next time.